Here we go. Okay, so guys, you don't know the difference, but I'm going to explain this to you anyway. We will never again this year do what we are about to do. What we're going to do today is we are going to cover chapter 3 in the next 55 minutes. Okay, and literally what we're going to do is we are going to page through, you guys are already there, right? We are going to page through chapter 3. And this is going to be you and me making sure that you remember all of this stuff that you learned last year. Now understand, along the way, we will run into things that we haven't done before, and that then becomes where I sort of take the lead and I teach you the things that you didn't learn last year, because we'll never do this again. We will never simply break open the book and go, let's do each page. This class doesn't work that way. So when we come back on Monday, we're going to get into chapter 4. We're not even going to open the book on Monday, and we're going to get into new material. But for today, we need to make sure that we're all on the same page relative to chapter 3. So guys, do this with me really quickly. You guys are at least a little bit familiar with this book because of your summer homework, right? But just do this with me really briefly. Are you guys on page 77? Okay. Huge text, right? And they give you the title of the chapter. Now turn the page again. Just sort of look at page 78 from a distance. Then 79, then go to 80. Then go to 81. Get a sense of that page. Then 82. Then as you continue on through 82, maybe take a look at 83. Then we go over to 84. And let's stop there. Because how is this book organized? Tell me more about subchapters. What are you seeing? Let's go back, guys, to page 78. What are you seeing? Talk to me about subchapters. What is your eye catch? You brought it up, so what are you picking up on?
So each chapter is broken down into separate, smaller sections.
And how do they show you those subsections? Exactly. Do you guys see that? 3.1. That is a subchapter where they're saying this is a big idea, but notice the font and the color. Black numbers, let's call that red. Red all caps lettering. Those set off the subchapters or the subsections of the chapter. Then guys, when you move down from there, is there another layer of organization? Do you see it? What does it look like? Red letters, but not all caps, and it doesn't have a number preceding it. And so we're another layer deeper into the material. And then guys, as you allow your eye to page through there, let's go to page 81. And at the top of page 81, it says indicating the states of reactants and products. Is that, where does that sit into the organizational structure? Like a second layer, right? It's not a 3.2 and it's not in all caps. But then when you go down again, you'll notice that now there's 3.2. It goes back to all caps and we've got another subsection of the chapter. Does that make sense? Okay, now go back with me to the beginning of the chapter on page 77. Obviously, the title of the chapter tells us the big idea. But then what do you notice beneath that as the text font goes from big and crazy spaced down to smaller and then on to 78? You'll notice, guys, that these chapters begin with 2 or 3 paragraphs that are before the 3.1. What do you suppose those are? The summary. It's the introduction to the chapter. Typically, they can be historical. They try to make what you're about to learn practical or interesting. This is about our good friend Antoine Lavoisier. He's a good-looking chap. But guys, that's your introductory stuff. So we go to there. Now, guys, let's do this. Let's go back to 78. We understand the way the chapters are chunked, right? Now let's continue down. And guys, what else catches your eye? 78, 79. We've got figures. And guys, you'll notice that these figures are referenced, if you will, by a number and then a decimal. So figure 3.1, figure 3.2, figure 3.3. Now guys, what you'll notice, for example, at the top of page 78, is embedded in the text where it mentions Lavoisier down at the beginning of the second full paragraph, it says figure 3.1. Can we just be honest about this? We just read right over that, right? If you were reading this thing and you saw figure 3.1, you wouldn't really look for figure 3.1, would you? You just keep reading. Guys, if you need to find these figures, understand the references are embedded in the text. Sometimes they're in the margins of the page. Sometimes, like at the top of 79, they're embedded in the page. Okay, now let's also look at 70, actually go back to 78. And also this is on 79. What else on this page is given a reference number? The equation. Guys, you'll notice that the synthesis reaction of hydrogen and oxygen becoming water is referenced as equation or reaction 3.1. Then you'll notice if you go on to 79, you've got the combustion reaction of methane, and that is equation 3.2. But as you go further into the chapter, and I'm not sure where we'll get to this, they will also reference mathematical equations. Similarly, they don't call it a figure, they just give it a number. So understand, sometimes I may say referencing equation 3.2. Do you now understand how to find that? Okay, so now guys, let's change the page and let's go over to page 80. If you flip over to page 80, you've got these blue spaces, right? What are those? Example problems. Guys, sometimes we'll work these in class, sometimes we won't. You'll notice that they follow the flow of the chapter. So if you need things to look at for reference, you'll notice that these things are denoted in blue. Okay, so now as we continue on, I'm on page 82. Now we've got a table. You'll notice that that table is also referenced by the same convention, table 3.1. Then on 83, we've got another blue space, and we continue on. Guys, go to page 86. Some people find these wildly helpful, some people don't. But you'll notice at the bottom of page 86, they have this thing that's called strategies in chemistry. They're problem-solving strategies, or they're concept clarification strategies. If you get into the middle of something and you're like, oh man, I don't know how to solve moles conversions. Maybe sometimes these strategy things are helpful and they're set out in green. Then as we continue on, if you turn to page 90, you'll notice on page 90 they've got this section that's called Chemistry and Life. It's not part of the content. But sometimes these things are fascinating. When we get into chapter 16 and we start talking about acids and bases and buffers, we're actually going to spend like 30 minutes and talk about the chemistry and life section there, because it talks about how your body knows how fast you have to breathe in order to not die. Why is it when you exercise, your respiration rate goes up? The reason is because as you exercise, your blood becomes acidic. As your blood becomes acidic, you've got this little pH meter at the bottom of your brain stem that measures the pH of your blood. And as the pH of your blood drops, as it becomes more acidic, your body knows that it's got to get rid of the carbon dioxide, and your respiration rate goes up. It's fascinating chemistry, and it has a lot to do with acids, bases, and buffers. And so we'll spend 30 minutes and talk about it. But we typically don't look at these chemistry and life sort of things. So what else do we got? We've got, continuing on, we've got lots of problems to solve. I don't see anything new through 96, 97. Guys, maybe let's do this then. Go back to page 103. End of the chapter. Wait, is that? Yes, it is. So guys, they do a nice job of this at the end of the chapter. They give you ideas on what the test might look like that covers this material, and they give you strategies on how to approach that. Then helpfully on the next page, you'll notice that they give you a summary of the entire chapter broken down just like the chapter into 3.1, 3.2, 3.3, and so on. These are wonderful places to go as you're thinking about studying for the test. Then guys, you'll notice that you've got key skills and concepts there, key equations, which is really nice to have. Now guys, there's one other thing that I want to talk with you about so that you understand this. Looking on page 105, these are the end of chapter problems, right? This is where your homework will come from every stinking day in this class. So turn over to page 106. Okay, so guys, questions 9 through 14. Where do those come from? Section 1. 15 through 20, those are section 2. 21, you get the idea, right? They're broken into sections just like the chapter. I point that out because I'd like you to go back a page. So guys, here's the deal, and let me just, I don't know if I meant, so the authors of this book, one of them is Eugene LeMay. He's actually a friend of mine. I know that sounds weird, but I was almost Eugene's PhD student at the University of Nevada, Reno. In the late 90s, I was actually thinking about leaving teaching and getting my PhD in chem, and I actually went out to Reno and got to know Eugene, and I was actually a PhD student of his, and then I met my wife and fell in love and canceled those plans and stayed in Utah. But anyway, I know Eugene, and I actually know how he put this book together. And here's what happened. Guys, you see this part on page 105 that says exercises and then visualizing concepts? Here's what happened. This book is in its 12th edition. And it used to be that the end of chapter questions started right here with what is now question 9. What happened was in 2014, the AP curriculum changed, and the major change was less math, more visualization. So what Eugene did was this. He added this section, the one on page 105, he added this section, but he didn't want to disrupt the flow of the questions throughout the chapter, so he stuck them all at the beginning. So the first couple of these questions are section 3.1, then 3.2, 3.4, and 5. So guys, this, and every chapter has these visualizing questions, and we'll do them, but we won't do all of them first because they're not in order. They're pulled out of the chapter, and this is a whole chapter's worth of visualizing questions. Does that make sense? Okay, so guys, that is what you need to do when you guys get into college and you start finding that you're learning most of the material from a class from a textbook. Guys, that's what you do with every one of your scientific textbooks. You sit down and figure out how it's organized. You figure out what resources are available to you in the book, and you figure out what your eye needs to pick up on in order to interact with the text efficiently. So you want to learn to do what I just did with you for every single scientific or mathematical text that you ever run into in college. So anything you want to add to the conversation, or are we good? Did you pick up on anything else? That was neat that you noticed those subchapters right away. You guys are good? Okay. So guys, now what we're going to do is this. Go back to the beginning of chapter 3. And slow me down when you need. And we are going to go through the entire chapter right now. Gets ready for this. This is a little bit exciting. So, guys, I do mean this in all honesty. If you, I'll add a little bit where I think it's necessary. There are some times where I'm just going to go, stop, we got to talk about this. But if it seems like we're all comfortable, we're going to keep going. So guys, looking at our textbook, we hit 3.1, which is all about balancing chemical equations. So let's talk. Guys, when you're balancing chemical equations, you understand what you're doing is putting the coefficients in front of things so that you've got the same number of atoms on both sides. So guys, why do we do that in the first place? What is the driving principle that tells us equations have got to be balanced? Come on.
It's where the same amount that goes in has to come out.
Yeah, and go ahead, what do we call that? Law of conservation of mass. Guys, matter can never be created or destroyed, so all the atoms on the reactant side have got to be the same as the reactants on the product side. And guys, I think most of you were probably successful with this. So certainly you're going to have practice on it in homework, but my question to you is, do we need to talk about it? Do you remember the tricks for balancing chemical equations? I don't know if you even, but when you learn to balance chemical equations, I gave you like 4 or 5 hints that make these easier, like balance polyatomics intact if you can. Do good. Do you want to go over those quickly, or do you? Let me just mention them quickly. So guys, one of the hints that I gave you was balance polyatomics intact if you can. So the idea is, like, if you had something like aluminum nitrate plus sodium chloride, and your products are aluminum chloride and sodium nitrate. We talked about the idea that you can balance the nitrates intact because you've got NO3 here and you've got NO3 there. Balance the nitrates. Don't balance the nitrogens and oxygens individually because the nitrates stay together. Do you remember that? Then Brandon's on to another one. Balance oxygens last. There's oxygen everywhere in chemistry. Guys, balance the oxygens last. Do you remember the one about the odd-even conflicts? Do you remember that? Yeah, so if you've got an odd number of atoms on one side and an even number on the other, double the odd number and then start over. Remember that one? What else did we talk about? I know we talked about the one that says when all else fails, just put a 1 in front of the first substance, see if you can get it to balance. If you can't, erase it, put a 2, see if that balances. Just do it by trial and error, and that can work as well. So guys, what else? Other things about balancing chemical equations you remember? You'll obviously have time to practice in homework, and if you need to ask questions on Monday, we can. You okay? Okay. So then, guys, moving along, we just did section 3.1. Let's go to 3.2. They call this patterns of reactivity. We last year just called it reaction types. So, guys, early on in the chapter here, they provide you 3 examples: combustion, synthesis, and decomposition. Do we need to talk about what these are or their general structures? Yes. Okay, so let's do this. Combustion is a hydrocarbon, which contains hydrogen and carbon, thus the name. So some amount of carbon X, some amount of hydrogen Y. That's reacting with oxygen because you need oxygen to combust things. And then do you remember the products?
CO2.
Yep. Good. Carbon dioxide and water. Then, guys, a synthesis reaction is a reaction that creates one product. You'll notice in the book they call these combination reactions. If you look at the top of page 82, they call these combination reactions. Guys, understand synthesis is the term that we use, and that's totally fine. The AP graders will understand what you mean by synthesis. And then a decomposition reaction is actually the opposite. That's taking one reactant and splitting it into its parts. I'm sorry?
Is that the one that has energy?
Well, they both do. So synthesis reactions tend to be exothermic. The forming of bonds gives off energy. Decomposition reactions tend to be endothermic because to break bonds, energy has to go in. We'll get into the energetics of this a lot more when we get into chapter 5, which is thermochemistry.
So like hydrolysis would be decomposition.
Hydrolysis is a decomposition reaction. And for those of you that don't know, hydrolysis is the breaking down of water, hydrolysis to break water. And if you're familiar with it, how do you get water to break down? Pass a current through it. You have to add energy to get it to break. You guys good on these? Okay. All right, so guys, moving on to this, atomic weight. So you don't need to grab, well, you know what? Actually, that's not true. You're going to want a periodic table at your disposal today, so you may as well just grab it now. All right, so we are on to atomic weights, looking at section 3.3, and this says formula weights, but it's it's the same concept. So guys, when we talk about formula weights, let's talk about the weights for atoms and the weights for molecules and see if we can pull this all together. So guys, let's talk about the weights for atoms first. So where are they found on your periodic table? They're the small numbers in red, right? On the periodic tables, again, that you'll have throughout the class, they're actually the one of two numbers that are on there, the numbers in the bottoms of the boxes. But guys, let's talk about what we know about these atomic weights. So first of all, what are the units for atomic weight? AMUs or grams. We'll talk more about that in a minute, but let's go with AMUs. So let's talk about carbon so we have sort of a common focus point. So guys, carbon element number 6 has a mass of 12.011, I think. Look at me. Oh. 1017. Okay, so it's 12 point, let's call it 01. So guys, the mass of carbon is 12.01 atomic mass units. So what does that number, let's call it 12, what does that tell us about a carbon atom if its mass is 12? But we're not going to go there yet. Let's stick AMUs. What do we know about a carbon atom if its mass is 12? 6 protons, 6 neutrons. So how does that work? Well, guys, what is the mass of a proton? 1 atomic mass unit. What's the mass of a neutron? 1 atomic mass unit. So we know that the nucleus of carbon has 12 of those things because its average mass is 12. So now how do we know how many of each? Well, remember the idea is carbon has an atomic number of 6, which tells us 6 what? Protons. And as soon as we know that there's 6 protons, we now know that there's also 6 neutrons because it adds that up to 12. We get that? Okay. Now, we now have to deal with the idea that these masses are not whole numbers because the atomic number does tell you the number of protons and neutrons. But if a proton weighs 1 and a neutron weighs 1, then why isn't the mass of carbon 12? Why is it 12.011?
Because it takes like the average of all the carbon atoms.
All, and that's the term is isotope. So guys, I pray that you know this, that the stuff inside your pencil is not lead, right? It was, but we found out that it causes birth defects, and so it's not anymore. This is graphite. Graphite is carbon. Graphite actually looks like this. It's fascinating stuff. We'll talk more about it later. But this is what graphite looks like. And guys, in graphite, we've got all these carbon atoms. And what do all these carbon atoms have in common? What do they all have in common? They all have 6 protons, because if they didn't have 6 protons, they wouldn't be carbon, right? So they're all carbon, so they all have 6 protons, but they all don't weigh the same. How can that be? Different numbers of neutrons. Some of them do have 6, but some of them have 5, and some of them have 8. And because that's the case, we have different isotopes of carbon. They all have 6 protons, or they're not carbon, but because they have different numbers of neutrons, some of them in carbon have a weight of 11. That means they've got 5. Some of them do weigh 12. That means they've got 6 neutrons. Some of them have 8. That's carbon-14. That's radioactive. You may have heard of carbon-14 radioactive dating. So guys, where does the number 12.011 come from? It's an average of all of the isotopes. Is that coming back to you? Okay, and so guys, we need to talk about that. So we understand now, let's make sure we're clear, why are the atomic weights not whole numbers, and we understand that it's because they have different masses. So let's do this. I want to find, let's not do that yet. Oh, they moved it. See if you can find, and do this with me, guys. There was a problem in here previously where they had us calculating average atomic masses. Where did it go? Or maybe I'm hallucinating. I am tired and I got bit by a dog yesterday. I could be rabid. I don't see it. Do you? Yeah, I don't, that's weird. Where did it go? That's really interesting. I don't know where it went. Anyway, I believe that there's a question on this in the homework. I think that you'll quickly figure out. Do you remember how to do this, where we said that the average atomic mass was the abundance times the mass? Add them up and then divide. What's that? Yeah, that's the abundance. So here, let me show you. So over here, come on. Let's see. So we'll go here, general chemistry. Here, average atomic mass. Whoa. Is this? There it is. Remember this? Where the average atomic mass is the sum of the masses times the abundances divided by 100. So for example, neon, and I'm not going to give you time to write this down, it'll come back to you. Neon is 90.5% neon 20, 0.27% neon 21, 9.3% neon 22. And in order to find out the mass, you take the masses times the percentages, and you add those up and divide by 100. Is that coming back to you? Okay, that's what we're talking about. So when you get to it in homework, if you get into it and you're like, oh man, I'm not quite sure, we can also talk about it a little bit on Monday as well if we need. Okay, so in my mind, guys, we understand this idea of why they're not whole numbers, and we understand average atomic weights or masses. We good to go? Okay, so now guys, moving along. Oh my goodness. Do you remember when you learned about the mole? So guys, thinking about this concept of the mole, and Brandon, this is where your brain was going a minute ago. Let's review quickly. Go back to carbon. Carbon has a mass of, let's call it 12.01. Carbon has a mass of 12.01 what? AMUs. One atom of carbon on average weighs 12.01 AMUs. But you guys learned something magical last year, where we found out that that mass for carbon, while it is this, and maybe this is worth writing down, while it is in fact true that one atom of carbon weighs 12.01 AMUs, we found out that that's not the only units for 12.01. That this number, 12.01, is also the mass of carbon in grams. But it's no longer for one atom of carbon. How many carbon atoms weigh 12.01 grams? Exactly, Avogadro's number, 6.02 times 10 to the 23rd carbon atoms. That's 602 septillion. Guys, 602 septillion carbon atoms also weigh 12.01, but now it's grams. But guys, the trick here is we know that this many atoms we call how much? 1 mole. And that was that magic moment that you had last year where you found out that if one atom of carbon weighs 12 AMUs, a mole of those carbon atoms weighs 12 grams. And based upon that, you started doing all sorts of dimensional analysis where you were converting between mass and moles and particles. And guys, that's what section 3.4 is all about, and we are not going to go over it because really the best thing to do is for you to just practice. And we're not going to do that together. You'll see some in homework though. Okay, so we're done with the mole. Can you imagine? That was fast. Go ahead. You'd have to show me. It's not coming back immediately. Okay. So guys, we're going to move forward. 3.5. Guys, or was this in the tail end of 3.4? It might be at the tail end of 3.4. Is it in 3.5? Okay, great. So guys, 3.5 empirical formulas. You learned this last year, so let's talk about it because this is a term that we're going to use extensively in this class. This isn't on the board, but write it down. So guys, what does the word empirical mean? And we understand that empirical formulas are simplified formulas, and we'll talk more about that in a minute. But empirical does not mean simplified. Does anybody know? Have you heard of the term empirical evidence? What is it? It's not. And that's the misconception that I'm trying to address. What does empirical mean? Exactly. Guys, the term empirical means based upon experimental evidence. So if you're an attorney, you would really like to be able to present the jury with empirical evidence. Because if it's empirical evidence, it's based by data that could or could not be irrefutable, but it's not an opinion. It's based on experimentation that can be reproduced. Now, Catherine, this is where things sort of get mucky-mucked, though, because when we learned about empirical formulas last year, we said that's the simplified formula, and you're right, but understand the connection is, in order for us to find empirical formulas, we have to do that from experimentation. And I'll show you the difference in a minute. So guys, an empirical formula is a formula that's based on experiment. It's based on experimentation. Now, when we talk about empirical formulas, here's what we need to be thinking about. Empirical formulas tell us the relative number of atoms of each element that make up a compound. And last year, you may remember, you learned to calculate empirical formulas. And let me remind you how we did that. If you don't remember, feel free to write this down. In order to calculate empirical formulas, what we did is we first of all assumed that we have a 100-gram sample. So if they give us percentages, like 50% carbon, we just call that 50 grams of carbon because we assume a 100-gram sample. So then what we do is we take these masses and we convert them to moles. And once we've converted them to moles, and this is where this might start to sound familiar, once we've converted those things to moles, we divide by the smallest number of moles, and that gives us the whole number ratio. Maybe that's the part that made this sound familiar. But guys, if you're writing this down and going, oh boy, I don't remember this, I'm going to show you an example in just a second, and I think you'll be better off. Bless you. You guys okay? I wonder if this is, oh, that's cool. The example in the book is actually vitamin C. We're not going to do that one, though. No. Bless you. Okay, so let me offer you this, and we'll solve this in just a second. You can write it down if you'd like. So guys, ethylene glycol is composed of 38.7% carbon, 9.7% hydrogen, and the remaining 51.6% is oxygen. The question is, what is the empirical formula? I'll let you write it down, and then I want to talk with you about this. And I think at that point, Catherine, if you're still going, wait, I thought it meant simplest, you'll understand the connection. Or for anybody else that isn't quite clear. So I'll give you a second to write it down if you want. You guys okay? Okay. So guys, first of all, does anybody know what ethylene glycol is? It's actually antifreeze. So the stuff that you put in your radiator is actually ethylene glycol. The problem with ethylene glycol is if we were to draw its chemical structure, it looks amazingly like sugar. And it's terribly sweet. They actually had this huge meltdown over in Italy about 15 or 20 years ago where Italian winemakers were actually lacing their wines with ethylene glycol to make them taste sweeter. And it turns out that people were getting horribly sick because it's also poisonous. The other problem with this, guys, is if you have pets, please do not leave antifreeze out in your, don't let your pets into your garage if there's antifreeze out there, because to a dog, this stuff is like candy and they lap it up and die. So be careful with ethylene glycol because it is a lot like sugar. You'll notice that the things that make it up are carbon, hydrogen, and oxygen, just like sugars, which are carbohydrates, right? Carbon, hydrogen, oxygen, water. So it's a lot like sugar. So the question is this, guys, if we have a jug of antifreeze, ethylene glycol, how do we find out the empirical formula? You ready? Here's the answer, and I'm just going to do this with my hands. This is how they figure out empirical formulas. What they do is they will take a sample of the substance, in this case ethylene glycol, and they will heat it up so hot that it not only boils, but the bonds break into its elements. Does that make sense? So you take ethylene glycol and you superheat it and it boils and then it breaks apart. And when it breaks apart, you've got carbon, hydrogen, and oxygen floating around in this vapor. And then what they do is they pass that vapor through a series of canisters. They're called scrubbers. And what they do is they weigh the scrubbers before the experiment. And then the vapor passes through the scrubbers. And the first scrubber collects all the carbon. And the next one collects all the hydrogen, and the next one collects all the oxygen, and what comes out the other end? Nothing, because that's all that was in there, right? If you have stuff coming out, it means you didn't scrub for all the things that are in the original substance. So after they do that, how do they know how much carbon was in there? You weigh the scrubber. You know what it weighed before. You figure out, you weigh it after. The difference is how much carbon was in there. Does that make sense? Then you weigh the hydrogen scrubber, then you weigh the oxygen scrubber, and by subtracting, you know the weights of the elements. So how do you turn those into percentages? What do you need to know? The weight of the original sample, right? So you start with 100 grams, and if you start with 100 grams of ethylene glycol, then the oxygen scrubber got 51 grams heavier, the hydrogen scrubber got 9.7 grams heavier, and the carbon scrubber got 38.7 grams heavier. Does that make sense? So why do we call these empirical formulas? Because the only way to find them out is by doing that experimentation, and that's why we call them empirical. Does that make sense? Okay, so we're going to keep going. So how do we calculate these? Well, guys, we're going to do this together. Do you guys all have this written down? Because I got to make it go away. So, guys, here we go. Do this with me if you don't remember. Never mind, I've got it right here. Okay, so we've got 38.7 grams of carbon. We've got 9.7 grams of hydrogen, and we've got 51.6 grams of oxygen. And now we've got to convert these to moles. 12.0 grams is 1 mole. 1.0 grams is 1 mole, and 16.0 grams is 1 mole. And now I do the math. Exactly. And that's the idea. The percentages are by weight, and if we assume that it's a 100-gram sample, then they're also by mass. So we've got 38.7 divided by 12, and that would be 3.23. And then 9.7 divided by 1, I think I can do that in my head. And then 51.6 divided by 16 is 3.23. So now we know the relative molar ratios. For every 3.23 atoms of carbon, we have 9.7 grams of hydrogen and 3.23 atoms of oxygen. The problem is in a molecule, we can't have fractions of atoms. So what we need to do is turn these into whole numbers by doing what? Dividing by the smallest number, which is 3.23. So divide by 3.23, divide by 3.23, divide by 3.23, and we get 1, and we get 3. And we get 3, and we get 1. And so then we've got CH3O. Now we understand that ethylene glycol is not a carbohydrate, because if it was a carbohydrate, this would be CH2O. That's where carbohydrate comes from, but it's awfully close. So guys, you good on empirical formulas? Because guess what? We're not done with them. We need to come back to this in just a second, but we need to teach you something new. Are you guys all caught up? Okay, this is going away. And here's what we need to talk about next. Oh, I'm drawing dots. We need to now talk about what are called molecular formulas. So guys, a molecular formula represents a molecule as it actually exists in nature. Now, guys, here's the thing that's interesting. Molecular formulas can be found from empirical formulas. We're going to do a lab on this. Maybe. We'll see if we can fit it in. So, guys, how do we do this? Well, to do this, we need to know the molecular weight of the compound. And I know that this seems weird, but it'll make sense in a minute. So let me give you the steps, and then we'll do it. So if we know the formula or molecular weight of the compound, here are the steps. Step number 1, you're going to calculate what we call the empirical mass. Then step number 2, you're going to divide the molecular mass by the empirical mass, and this will then give you a multiplier that will give you the molecular formula. And now you're sitting there going, what does that mean? I will show you. So guys, once you're all caught up, I will show you what we're talking about. And then we've got one more thing to do, and then a big thing to do, and then we'll be done. That's weird. Okay. We're okay. All right, you guys all caught up with me? Okay, so guys, let's go back here. I'm going to make this go away. Is that going to cause anybody panic? Okay, so I think I can do this. Yep, nope. Oh, I can't. Just a second. I got to do this. Now I can bring that back. Okay, so guys, we did this calculation, right? And we figured out the empirical formula for ethylene glycol, CH3O. You good? Is that ethylene glycol? No. Not necessarily. It could be, but many times it's not. So if you could get a thing of antifreeze, and if you could grab an ethylene glycol molecule, it might just be a carbon bonded to 3 hydrogens and an oxygen. But it isn't necessarily. The only thing that we know about ethylene glycol for sure is that it will contain 3 hydrogens and 1 oxygen for every carbon. This is simply the ratio. We don't know if this is really the molecule. So how do we figure out what the molecule actually is? Well, guys, what we've got to do is we've got to do a little bit more math. So check this out. Write it down in your notes. It says this. What is the molecular formula? What is ethylene glycol if it weighs 62.1 grams per mole? What is this stuff if it weighs 62.1 grams per mole? So guys, obviously the critical piece here is the 62.1 grams per mole. You okay? Okay, so we're going to go here. We're going to go here. I'm going to switch to red so that this stands out. So are you all okay with the idea that this is not ethylene glycol? This is just its empirical formula. Okay, now let's figure out what ethylene glycol actually is. So to do that, and you've got the steps in your notes, step number 1 is to figure out the formula mass. Or I'm sorry, the empirical mass. So guys, here we go. What is the mass of carbon? 12. What's the mass of hydrogen? 1 times 3. What is the mass of oxygen? 16. So we add those up, and we've got 15 and 16 is 31. So the empirical mass is 31.0 grams per mole. So what do we do with that? Well, guys, here's what we're going to do with this. And this is not an official equation, but this is the idea. We need a multiplier, and that multiplier is equal to the molecular mass divided by the empirical mass. So what does a molecule of ethylene glycol weigh out of what you wrote down just a second ago? 62.1 grams per mole. What is the empirical mass of ethylene glycol? Well, that's this, 31.0 grams per mole. And if you do this math, it's a 2. So what does that tell you? Well, it tells you that the molecular mass is the molecular formula is twice the empirical formula. So then what you do is you go back to the empirical formula and you double it. So it's C2H6O2, and this is what ethylene glycol actually is. What do you think? You okay? Questions on that? We got one more thing to do if you're good. You okay? Okay. So guys, we've got one more bit of information to review, and then we're going to do sort of a culminating experiment, and then we are going to wrap this up. So guys, it goes like this. The chapter runs out this way. So 3.6 talks about what we call quantitative information in chemical equations. And this includes mass-mass problems. Mass-mass problems are dimensional analysis problems that begin and end with mass, thus the name. These things require, remember, stoichiometric relationships. Then, guys, in 3.7, it talks about limiting reactants. What do you remember about limiting reactants? Why do we call them that? Go ahead. Yeah, go ahead.
Because, like, if you're making a reaction,
Mm-hmm.
the substance that you have the least of
Mhm.
is going to be the limiting reactant because it's going to determine how much of the end molecule
Product,
yeah.
that you can make. So it limits the extent that the reaction can go. So we call it the limiting reactant. Notice, though, that when we talk about the least amount, that's by moles and not by mass. And guys, so a limiting reactant is the one that's consumed first. But because we talk about limiting on a mole and not a mass basis, you need to know how to calculate limiting reactants. And you may remember this calculation. You take the mass, convert it to moles, you divide by the coefficients from the balanced equation, and then the smallest number is your limiting reactant. And then, guys, we ran into, and I know this is going fast, we'll have a chance to go back over it in a second. Then we had one more important concept. When we were done with this last year, talking about these concepts, we brought in this final thing, theoretical yields. So when you run out of a limiting reactant, as Ethan got us thinking, and I'm glad you made this connection, when you run out a limiting reactant, that limits how much product you can make. The amount of product that you can make, given your limiting reactant, is what's called your theoretical yield. And so a theoretical yield is the maximum amount of product that you can make given the limiting reactant. And then you may remember from there we calculated percent yields. And if you don't remember, percent yield was equal to your actual yield divided by your theoretical yield times 100. So guys, as you're writing all of this down, let me just sort of whisper into your ear a little bit. Some of you right now are going, man, I don't know how, but I remember all of this, and this is familiar, and it's coming back to me, and this is great. That's cool. Some of you right now are going, oh crap, I don't remember a stinking thing. I wonder if my counselor is available to do a schedule change. Guys, that's what makes this first unit, well, one of the things that makes this first day weird is that everything that we just went over, except for molecular masses and molecular formulas, all of this was review. And each of you is going to have a different experience with that review depending on what you retain from last year. So guys, please don't look around the room when we do what we're about to do and think to yourself, I'm stupid, everybody else gets this, and I need to get out of here because I don't remember anything. You may not remember anything, but guys, it means you just need more time to come back up to speed. You're okay. Also understand that some of your classmates are just really good at faking it and they're as lost as you are. But guys, understand it is going to take some time for some of you to come back up to speed, but trust me, it will happen. So with that said, you've got 14 minutes to solve this question. Don't write it down, just leave it on the board, but solve it. So guys, here we have a reaction. Let me zoom into this so that you can see it better. So I've given you the balanced equation. I gave you the balanced equation and I told you this. Assuming that you start with 25 grams of cyclohexane and 25 grams of oxygen, what is the limiting reactant? What is the theoretical yield for adipic acid? And if you only get 33.5 grams back, what's your percent yield? So let's decode this first. What is that? You have no idea. What is that? We know that's oxygen. What is that? We have no idea. What is that? It's water. Guys, you need to get used to looking at balanced equations and going, I don't know what most of this stuff is. Then you get through it. Because guys, if you then read the question, you'll notice it says, assume that you use cyclohexane. And if you're using it, doesn't that make it a reactant? So is this cyclohexane? No, you know that's oxygen. So what does that have to be? Cyclohexane. Hex is 6. You may have figured that out. Now as you read on, we get down here to the second question, and it says, what is the yield for adipic acid? Yields are things that are produced. Is this adipic acid? No, but guess what that is? See, you don't need to know what these things are. You've just got to be able to contextually figure it out. So guys, based on that, answer these 3 questions. What's your limiting reactant? What's your theoretical yield for adipic acid? What's your percent yield if you only got 33.5 grams? You now have 12 minutes to figure this out. So guys, I purposefully wanted to give you about 90 seconds to sort of get started. Some of you are writing furiously. Some of you are already poking your calculator. Some of you are sitting there going, I have no idea where to start, and you haven't written anything down on your paper. That's fine. Keep working. But if you're sitting there going, I don't know what to do, you are going to find that when you sit down to the AP test, every question that is on that test, after you're done reading it, your first response is going to be, I don't know what to do. And then you're going to do things and you're going to pass the test. Guys, one of the things that you've got to learn to do in this class is learn how to push through failure and learn how to solve things that you initially don't know how to solve. And sometimes it just means you need to start moving your pencil. So guys, if you're sitting there right now and you're like, crap, I don't know what to do, maybe your first move is write down everything you know. Write down the balanced equation. Write down 25 grams of cyclohexane, and now that you know what cyclohexane is, put C6H6. Write down 25 grams of oxygen and write down 25 grams of O2. Start. And you'll find sometimes that if you start, it just gets the process started. Understanding that may not be the case for you right now, not because you can't ever do this, but because you don't remember, and that's fine. Because this is not stuff that I directly taught you. A lot of this is drawing on what you remember from last year. You have about 5 minutes left, guys. I have 2 minutes. And then we'll solve this together. Actual divided by theoretical times 100. Otherwise what? If you...
Yeah, I was using percent error. That's what it was.
So guys, you have 1 more minute. Okay, so guys, whether you're done or not, I'm going to ask that you join me, because what I'd like to do is I'd like to model for you a little bit this idea of what do you do when you're stuck. And guys, I really, you're going to get stuck a lot. And you're going to sit down to solve these problems and you're going to be like, I don't even know where to begin. And guys, I'm really serious about this. Just begin by even just collecting information. So if I were stuck on this problem, the first thing I'd do is recopy the balanced equation. Just that experience of writing out the formulas that you're working with sometimes can get things moving. But then what I would do is this. Because chemistry many times is a mathematical subject, it's sometimes sentences don't necessarily lead to math. So what I like to do is I like to distill. So I don't have the original question up on the screen because I need the space. But as I started to read through the question, what I did was this. I said, okay, assuming I have 25 grams of cyclohexane, I'm going to write that down. 25 grams of cyclohexane. And I react that with 25 grams of oxygen. And again, how did I know what cyclohexane was? Process of elimination. And then I gathered all of that information. But I just keep going. And I'm like, what other information is given me? So I also know that I had 33.5 grams of adipic acid. And I knew that also by process of elimination. And so I'm distilling what I've given down to something that's more manageable rather than a string of sentences. Once I've done that, then I need to start thinking about how to actually answer the question. And the question is asking me, what is the limiting reactant? And I'm like, okay, I remember how to do this. I know that limiting reactant is a mole relationship. Remember when we talked about building bicycles last year, which was a horrible example, but we said frames and wheels and seats make bikes, and we talked about the idea that when we put bikes together, it goes by parts and not by weight. I don't know if you remember. Anyway, this is a moles thing, so we got to convert to moles. So I've got 25.0 grams of C6H6. And I've got 25.0 grams of O2. And I've got to convert both of those to moles. So 72, 78. Oh, I was thinking benzene. Sorry. Wrong stuff. 84? Okay, thank you. So 84.0 grams is 1 mole of this. 32.0 grams of this is 1 mole of that. Can you guys feed me the numbers? What's this to 3 sig figs? 0.298 moles. And this one? 0.781. Can you guys confirm or deny?
Yep.
Good? Okay. So now we know that in those 25 grams of these substances, we've got 0.3 of a mole of cyclohexane and about 0.8 of a mole of oxygen. That doesn't yet tell us, though, that we have less of the cyclohexane, so we'll run out of that first, because it may not react together 1-to-1, and it doesn't. For every 2 moles of this, we will consume 5 moles of this. We need to account for the fact that they don't react together in 1-to-1 ratios. So, doing the math, 0.298 divided by 2 is 0.149, and then 0.781 divided by 5 is 0.156. Now the smallest number is the limiting reactant, and guys, remember, you've got to write a statement that says the limiting reactant is cyclohexane. You guys good? Okay, now question number 2 says this, and it comes back to what Ethan said very well. Now that we know which one is our limiting reactant, we need to think about, why do we call that a limiting reactant? Because it limits how much product we can make. Now, which product, given question number 2, do we care about? The adipic acid. Do you see where we're going? So now the next question, and guys, you need to get used to this. This is the way the AP test goes. There will never be questions on the AP test that's one standalone question. It'll be question 1A, 1B, 1C, 1D, 1E. They're these multi-level questions. So now that we know the limiting reactant, we're not done with that, because we need to know what the limiting reactant is to figure out how much adipic acid we can make. Now we have another calculation, and it starts with our limiting reactant. 25.0 grams of C6H12. Why did I start there? Because that is what will limit the amount of adipic acid I can make. Now I'm going to do a mass-mass problem, and I want to know grams of adipic acid. You'll notice that I didn't write it out. That's a waste of time. Now let's get into this. So guys, this is a mass-mass problem. We already know that 84.0 grams is 1 mole of C6H12. Now we need to know the mole-to-mole ratio. We need to know, for some moles of C6H12, how many moles of adipic acid will I produce? And where do we get that mole-to-mole ratio? Balanced equation. So it is a 2-to-2 ratio. Now guys, 1 mole of adipic acid is how many grams of adipic acid? Well, now we need to write out the formula, because we need it to come up with its mass. So it's H2C6 H8O4. What's that weigh? 1 or something. 140. Can anyone? 146? All right. 146, 6.0 grams. And now we do the math, which is easier with a calculator. And we go 25 divided by 84 times 2 divided by 2 times 146. 3 significant digits, 43.5 grams of adipic acid. Is that okay? Okay. And then guys, the final step, I'll just do it really quick. Percent yield is equal to actual divided by theoretical times 100. Our actual yield is this, 33.5 grams. Our theoretical yield, which conveniently we just calculated, is 43.5 grams times 100. Do the math. What's it work out to? 76.5%. Give or take. You guys okay? So gang, again, some of you were going, hey, I remember this. Some of you were going, wait, did I take chemistry last year? Guys, understand, progressively over time, this stuff will come back to you. So, let's do the pledge. Oh wait, open the blinds. Here we go. There we go. Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation under God, indivisible, with liberty and justice for all. Then we do the announcements. Thanks, guys.
This Saturday, cross country has to be at Westlake, and the race will be starting at 8 a.m. Football will be here on Saturday. JV plays Bishop Dorman. For Barnwood plays Saturday at 7. Then we have food starting all the way up to dinner. Tomorrow, Friday, on the soccer field, there will be a movie night. Bring their blankets and chairs, and it will be free, but concessions will be sold clothing. Starts at 8:30. Back to school pool party at Sarah Pool next week, Thursday, from 7:30 to 9. Cost is $3. Come and go with friends. Or mine, Mountain View, and Club Rush is next week, and club will be set up at the conference at 5 o'clock. So you can go around and sign up to get involved. Get your parking passes today. If you want to be able to park in the parking lot, you will need to buy the parking pass for $10 at the financial office. You will be ticketed if you do not have a pass. The back to school open house is tonight from 4 to 8 p.m. A sophomore student parent presentation start at 5:30. Junior and senior student presentation start at 6:30. Picture day is next week, August 30th. So pick out your outfit because you want to look good. It's going to be on your ID card. Have a great day, guys.
Okay, guys, homework. This is your homework for tonight. You want to write this down. These are all end of the chapter questions. You are going to do questions 3, 5, 7, 14, 19, 25, 37, just 45A, 49, 57, 63, 79. These are all at the end of chapter 3. Guys, in addition to that, there were 2 other things that you're going to do. I'll let you write these down and then I'll share those with you. Okay. Good heaven.
Oh, sorry. I was like, sorry.
At the end of chapter 3, you're going to do 3, 5, 7, 14, and on. Guys, in addition to that, there's 2 other things that you're going to do. We're done with chapter 3. The next thing that you're going to do is you're going to outline chapter 4. This is not due on Monday, this is due on Wednesday. I want you to outline chapter 4. You understand outline formats that go Roman numerals, capital letters, and then subpoints, 2, and then a B, and then another Roman numeral. You know what I'm talking about, right? You know how to do outlines. Yeah? Catherine figured it out. Guys, how are the chapters organized? Remember how we started the day? As an outline. So this would be, well, 4. This would be 4.1 and whatever that is. And remember, this is the part that's in all caps in red, right? Then as Ethan called it, you called it like a sub-chapter or something like that. Your first sub-chapter is letter A, and whatever that is in capital lowercase red. And then beneath that, what are your 1s and your 2s and your 3s? The information in the chapter, right? These books are set up as outlines. That's why we went over that at the beginning of the day, and that's why I'm having you outline chapter 4 so that you understand that these chapters are set up as outlines. Does that make sense? Okay, now guys, you've got one other, and realize that's not due till the 30th, but guys, remember, these are weighted really heavily, right? Do a good job, turn them in on time. Don't lose these points, because these are the points that will save your grade. The third thing that you're going to do is this. Let's make sure it is on page 121. Yeah, guys, on page, and you may want to go there right now. On page 121, you are going to summarize table 4.1. If you're on top of things, you should be able to take table 4.1 and condense it down to 4 to 6 sentences. And some of you picked up on this, right? There are huge trends to the solubility rules. All nitrates dissolve in water. All acetates dissolve in water. All halogen-containing compounds dissolve in water unless they're bonded to silver, lead, or mercury. All group 1 salts dissolve in water. There's all sorts of trends. See if you can find them and summarize them. No, don't type it. Guys, don't type anything in this class. Everything should be written by hand because your AP test will be written by hand. Yeah.
And then when you say outline chapter 4, you don't just want us to write the headings, you want us to write the heading and the description, right?
Yeah, so like if you're if you're starting in chapter 4, the first thing that you're going to, well, here, I even did it in here. So what I would do is electrolytic process. And then I'd continue on, and then where's my next, and then down here, that would be my numeral. You know what I'm saying? Okay.
So, for the Roman numeral and the first letter,
Yeah.
do we just write the heading and then in the numbers?
Because that's what it's about, right? They've already done the work for you.
Okay.
Okay. You guys good?
So by outlining, you just write down like all like
What we just talked about
But then you summarize in the like.
in the numerals. Okay, guys.
That's sort of like it.
So the chemistry hat comes off.
So wait,
Um,
the summarizing the table on page 121 is that due?
That's due, yeah. So guys, the summarizing of the table is due next time. So I know you want to pack up. You've got 45 seconds and then we're going to talk. That's fine, yeah.
In a way that shows significant summarizes significant.
Okay, guys, so let's talk. We need to go over this stuff. This is different, so let's make sure we're clear. If this were next week and we were running Pride the way it should run, what happens when we start saying the Pledge of Allegiance?
Eyes.
The people with eyes are walking out the door. You can say the pledge as you wander down the halls. Then, guys, we listen to the announcements at 11:55. The people with acceptable grades leave. Everybody else stays. Typically, I have more AP students that end up trapped in Pride than in my general chem classes because you guys are smart enough to know you can make your grades up later and you just get lazy and your grades slough. All right, anyway, so with that said, these are the things they want us to talk about. First of all, cheating. We do, and you can read this in the handbook, we do have an academic honesty policy. I had a hand in creating it, and I'm not exactly quite sure what it means or what it says. It's not worth going there. So understand that there are supposed to be some systemic things in place relative to academic honesty, but I think for you the issues are deeper because of the kind of people that you are. You're not looking to get around this. you're looking to protect your integrity. Cell phones. This is something you do need to understand, and I understand that at Orem High we're really lax about following through on policies, but this is one that somebody could call you on and it could get ugly. I mean, cell phones in classes, different teachers have different policies, right? The thing that you've got to be really careful about, and this is the way it says, this is the way it's stated in the law. Anywhere in the school where you should have a reasonable expectation of privacy. That's locker rooms, that's bathrooms, places like that. If you get out your cell phone in places where people have a reasonable expectation of privacy, not because you have a phone, but because your phone has a camera, it can cause issues if people think for some reason you might be taking pictures of them. Be careful. So they want us to talk about clubs. We are having Club Rush next week. Look for that. You heard on the announcements, if you need a parking pass, you've got to pay for it. Do you guys even use lockers anymore? No, okay, so if you want a locker, you can have one. We do have a lost and found. I encourage you, if you lose anything, to not go through the lost and found, because that's where I do most of my Christmas shopping. So just leave it down there. I'll give it to my kids. Everything will be fine. And then finally, no, seriously, it's down in the office. If you lose something, go down there first. And then just a second, visitors. Guys, this is really more for the adults than it is for anybody else. But you could be a part of this as well, I think. If you're going to bring a visitor onto campus, you need to have them check in at the office. As you learned last time, we're doing safety hopefully better. And one of the things that they're really encouraging us to do is confront people in the hallways that we don't know. A lot of times when they've had things go bad in schools, those bad people wandered the school for some period of time before things started happening. And there's some evidence to suggest that if somebody would have simply confronted that person, not like, hey, get out of here, but hey, can I help you find whatever, there's the possibility they may have just left. So you will see that adults will be confronting, for lack of a better term, people in the halls, which means if you're bringing someone on campus, make sure that they get a visitor tag. And also, if you see people in the halls where you're like, ooh, that guy I don't think he goes to school here. If you're not comfortable confronting them, please come and get a teacher, and we will. We're sort of policing our own school. So the other things they want us to talk to you about, blue and gold Fridays, wear blue and gold on Friday. Ultimate Tiger. I love this. Right. That's why I love it. So, Ultimate Tiger has been something that has been a part of Orem High School tradition long before I got here 25 years ago. The administration decided that they wanted to take Ultimate Tiger and turn it into something different. Thus Brandon's question, which one? So if you want to be the Ultimate Tiger that is not governed by the administration, you can figure that out on your own. If you want to be the Ultimate Tiger that you can actually get your name in the yearbook for, there's actually a thing where you have to go to events, you've got to do service, you've got to sing the school song, you've got to participate in Blue and Gold Fridays, and then write something about why you love the school. So if you're interested in that one, you need to go talk to, does anybody know whom? Menlove. Yeah, thank you. And she's managing that. And then finally, guys, the last thing to tell you is that tomorrow we are on an assembly schedule. We're having a welcome back assembly. And then next week with Pride, we are going to run Pride reports next week. So if you want to go to a teacher's class, we're doing eyes, but we are not retaining anybody based upon grades. you can thank me later because that was actually my suggestion in the meeting that was trying to figure out how to do this. The administration wanted to start doing Pride next week. And I'm like, good night. I've only turned in 2 homework assignments, and if a kid didn't turn in one of them, they're failing. What if we let everybody go to Pride but still do I's? And so that's what we're going to do. So next week, everybody will get Pride, but if you want to go see a teacher, you can still ask them for I's.
Thank you.
You guys just survived your first day of AP Chemistry. You okay? Yeah?
Oh, yeah.
Yeah, it's great. It's a lot. But guys, understand you will never have another day like today. When you come in on Monday, we're going to start chapter 4, but it is not going to be open your books. But understand I should tell you this. When the bell rings on Monday, the very first thing that you want to do is open your books. But the reason is you're not going to open to chapter 4. You're going to open to the end of chapter 3, and we're going to answer all of your homework questions. Then, typically, you would put your book away. I'm going to have you keep it out because I'm going to want you to be able to reference the table that you summarized. But we are not going to use the book as a teaching tool. It's going to feel more like you thought class should. Yeah. People already have. Yeah, you're welcome to do it even now. So yeah, if you want to get that out of your hair, yeah, before after school, Pride if you'd like to stay, whenever you want. Just if you could let me know ahead of time, that would be great. But if I'm here, you can take it. So no, before the end of the quarter.
Memorial?
Yeah, Memorial Day. Yeah, in May. I think you meant Labor Day. Yeah, no. So guys, we've got about 8 minutes left. Talk amongst yourselves.